good morning, everyone. So in this lecture, I'd like to continue the relation between quantum entanglement and the area safety correspondence, and especially first, I'd like to introduce the idea of entanglement wedges, which is used nowadays in many places, and I will give us a very brief, quick overview of this idea, and then in this slot of this morning session, I'll also talk on the holographic dual of boundary conformal field theory, BCFTs, which is also related to recent story of island and black hole information. Okay, so let me begin with entanglement wedges. But this idea of entanglement wedges appears when we think about quantum correction to holographic entanglement. Quantum corrections to HEE, holographic entanglement entropy. So as we saw yesterday, the leading order, so we're talking about the classical gravity theory. Then we have entanglement entropy, simple entanglement entropy formula, which is like just area of this minimal area surface, right? Divided by 4 G Newton. So this is the order 1 over G Newton. This is a classical gravity. And this is actually in CFT, this is correspond to order n square, right? Order central, or maybe we can also say order central charge in 2D CFT. It's n square of gauge theory. This is the leading order. But the question is, what about higher order? And this is actually worked out by Faulkner, Lukowitz, Maldacena. 2013. And so what we find is simple formula. Actually, so this is come from gravitational degree, obviously, classical gravity. But there are some actual quantum correction because we are talking about order 1 corrections. And that actually is simply given by bulk entanglement. Right? This is really quantum, right? This is really quantum gravity effect, right? Quantum gravity. But this is about MA, right? This MA is, I will explain this, but this MA is called entanglement wedge. So what is the MA? So MA is, so that's right, circle, and we are talking about region A, right? We're talking about region A. This is region A. And we have some bulk minimal surface which calculate entanglement entropy as we saw yesterday. So this is a gamma A, right? It's gamma A. So this is a minimal surface. So I can also put minimum, right? And so this area gives the entanglement entropy, and this is exactly this part, right? Tells us. But we are talking about the higher order 1 over, 1 over n corrections. So this order 1 means, of course, also this means order order 1, right? In 1 over n expansion. This is quantum effect. Or 1 loop. This is 1 loop, right? For 2 loops, you get a G Newton, right? Higher power G Newton, and so on. And the MA, this region called MA is entanglement wedge, right? This is entanglement wedge. It's called entanglement wedge. This is here is a region. So we're talking actually this region. The region which is surrounded by A and gamma A. So this is actually MA. So boundary of MA is same as A union gamma A. So this is an entanglement, which is the region which is surrounded by original subsystem A and the minimal surface. And so this is actually intuitively, this is not so difficult to understand. Right? Because you can remember yesterday's derivation of holographic entanglement entropy, this part, right? So we introduced some 2 pi n replicatoric, right? We have some 2 pi n periodicity here, and that they actually, roughly speaking, that they extend in the bulk, right? And then we can calculate, you can imagine, you can calculate this replicatoric for full gravity partition function, then you get 2 pi n periodicity here, right? So then you get just a bulk replica calculation, right? Then that picks up, entanglement entropy for this region, obviously. And the reason why we have an extra term, this comes from really purely gravitational effect. And nowadays people say this is kind of H mode contribution. This is very typical to gravity, right? And in usual quantum field theory, we don't have any contribution to entropy at classical order, right? If you can imagine some classical scalar field or classical fermion or classical gauge field, you don't have any classical contribution to entropy. Right? Only if we quantize theory, we get a quantum entanglement entropy, which is precisely this one. But in gravity, because gravitational action is somehow topological because it involves curvature, and we can pick up some Euler number of this horizon area. And that gives basically gives this classical contribution, which is also called H mode, because if you have some gravity, if you have some gravitational theory, artificially you cut into A and B, then some hidden excitation mode, hidden mode is localized here, right? This is H mode, and this extra guy contributes to this area. And this is much like analogous to topological insulator or quantum Hall effect. That is quite interesting aspect. But I think I should say we still don't know what precisely this H mode means even at present. So this is a quite interesting frontier of this topic. But at least we can evaluate entropy. Okay, and then so this is a kind of I just talk about quantum corrections, and then we get this idea of this entanglement. So full entanglement entropy for CFT in CFT is actually computed from this information bulk entanglement between this side and the other side. Actually, there are questions. So are there any checks for one loop orders through other approaches? One loop order. Yeah, actually we can calculate both sides, CFT side and also this one loop. This is concrete calculation in gravity side, and they precisely match. There are many works in this direction. And but this is originally Strominger buffers approach is like just black hole entropy. It's a little bit different. Right? It's about black hole horizon. And also in that case, you can talk about one loop correction to black hole entropy, and that also agree with quantum field theory calculation. Gravity calculation and also CFT calculation. That's also no. But what I showed is sort of generalization of that idea, including some surface which is no longer black hole horizon. So anyway, we can check both sides anytime. That's right. And so this is a one loop correction. So yeah, now somehow we encounter idea of entanglement, which also I should mention that in the end, if we talk about full order, we have some idea is that in the end we expect this minimal of this area of some surface, and full including interaction, full bulk entanglement entropy, and take we take a minimization of gamma A. This is this minimized surface is nowadays called quantum extremal surface. And but I'm not going to details, but this is quite also very important application to recent idea of black hole information. But I just talk about clearly because we can show precisely clearly up to one loop order. So but higher order you take into account all interactions, all bulk entanglement, and plus this H mode contribution, and minimize it, then we get a full answer to CFT entanglement entropy. Okay, but I'm not to go. I don't want to go to the details of this guy. Okay, so now I go to this more precisely what about entanglement. So how we can use entanglement?
Can I ask a question?
Yes. Yes.
To include by including all higher loop corrections, you mean we include correction from D instanton?
I think, yeah, we should include everything. Yeah, you're right. Yeah, in that sense, it's, you know, it's not, probably it's not possible to compute all order. That's right. Yeah, this should be, you know, this formula should be non-perturbative. Yeah, but yeah, there are many ambiguous issues because of, you know, lots of corrections and so on. But people believe this is to be true. But only so far, I think it's a concrete calculation only done for one loop level. And in that case, we have perfect match. Okay. And so now I just want to explain how this entanglement is useful, right? What's the meaning of entanglement precisely? So let me write some picture. So this is somehow the same picture which we had before. This region A is here, and we have some minimal surface here, right? And we talked about this region, right? So this is MA, and we have some. This is entanglement, right? This is entanglement. MA is entanglement. Okay, and the claim is following, right? So what I want to say is following. So we are talking about some correspondence, right? Because ADS-CFT is correspondence between CFT and gravity. So this is the CFT side, and this is gravity. So we have CFT side and the gravity side. And then, so we are talking about some information which included region A. Region A means just this region, right? And CFT information. And this is actually characterized by reduced density matrix. Reduced density matrix. And then, in the gravity side, this corresponds to a region MA, right? Entanglement wedge. And in gravity side, we have this bulk density matrix, reduced density matrix, which localized on MA, right? This guy captures information in this region, and this guy captures the boundary information localized on it, right? And the idea is these two guys are dual to each other, right? Correspondence. There are one-to-one correspondence between them, but of course we have some comment that we would like to take some low energy. Both sides. For example, gravity side, this is obvious, right? Because we are talking super gravity-like approximation, right? And this classical gravity dual, we start with some classical gravity-like, you know, classical space-time given by metric, not fluctuating metric, just fixed metric. That means we are looking at some low energy, like some Planck, much lower energy than, much lower than Planck scale. And equivalently, because we are cutting off some information of quantum gravity, we get rid of high energetic information of quantum gravity. That means also we should do the same thing for CFT. And we are, in CFT side also should be, you know, low energy. But if we restrict to this low energy level, so people also call this in connection to quantum error correction. So it's like people also say this is called subspace. But in my talk, this is not essential. If we restrict to some subspace, low energy subspace, and then we can have some duality between information in CFT side, in more precisely low A information is correspond to low MA information in the bulk. And okay, so there are some questions. Okay, is the surface here supposed to be classical? Aha, okay, good question. And so if we look at just the, leading order, this is just classical minimal surface, but in general, if we talk about full order, right? Because we are talking about including all, many one over n collections, then this should be quantum extremal surface. This should be quantum extremal surface. And is MA, SMA is divergent? Yes, this is also divergent. Okay, so another question is that this guy, this guy is entanglement entropy. This includes UV divergence. However, this divergent, you can absorb in the first term because you can renormalize Newton constant. And in that sense, in the end, bulk contribution you can regard as just finite contribution because in gravity, once you couple theory to gravity, everything should be finite, and everything should be renormalized. Right? We are string theory, for example, it's a UV finite theory, so we expect that should be fine. Okay. And then what I wanted to say is that anyway, this is the main thing I want to say, but I will give one more evidence for this later. But people, by using that, people argue this is sort of proven. And also I have another kind of derivation of this in a few years last year, actually 2 years ago. If I have time, maybe I can give some explanation of this, but I'm not completely sure. But I want to tell you the main claim of here. So the main claim is, so main claim is that this low A CFT is related to, so just write it here, same one, basically MA. This is very important. And so people who use the word called bulk reconstruction. So bulk reconstruction means this direction. You can by assuming some information, the information in CFT region limited to region A, you can reconstruct bulk geometry, bulk theory, bulk gravity. Right? Because if this duality is true, then we can just reconstruct higher dimensional gravity background from just CFT information. And this is a basically bulk reconstruction. And you can, for example, I'm not going to details, but you can explicitly find a local operator, for example. You can put some, you can have some bulk field, acting on some point, and then such a state we can realize, from some non-trivial operator, which is smearing over region A. And this is actually called HKLL like map. I'm not going to use it, but there are explicit map also for bulk reconstruction. You can just using the operator in CFT, you can reconstruct bulk gravity Hilbert space. And one more comment is that, so more precisely, so entanglement wedge is defined following way. So this is not, because it's a bit confusing, because it's not, doesn't look like wedge, right? This looks like just some region, right? It doesn't look like why entanglement wedge is wedge. So it's just the right picture. So this is let's assume some kind of global ADS. My ADS 3 is fine. And we talk about time slice. We talk about some time slice. This is tau equals 0. And so we choose some subsystem A to be here. Right? Here. This is subsystem A. And then you have some gamma A. Right now we include time direction. Right now we include this is a real time. So I should write t. Right? T. This is a t direction. Real time. I'm talking Lorentz ADS. And that case, so that the way to do this is like this. So we have like this, this is MA, right? Entanglement wedge. But actually, this is not precise entanglement wedge. Let's start with the MA. And then what we do, we consider a sort of, domain of dependence here, of this MA, right? So causally related part, right? So the region which is fixed completely by MA is domain of dependence. Domain of dependence is completely fixed by MA. Because it's a point you cannot, this looks like space-like, so information cannot come outside of MA. It's all the time like geodesic connected to MA. And so this blue region, right? We have this blue region, right? This blue. So this blue region looks like this kind of wedge, yeah? So it's like really come from here, and this is exactly what people call entanglement wedge. I just wanted to comment this, right? But most of many works and also my work, we restrict to static space-time, and then we can ignore time direction, and then essential part of essential part of entanglement, which is like this region. So that's the reason sometimes people call this is entanglement. But more precisely, this full region, this region is entanglement. And if we are yes,
is the intersection of the bulk domain of dependence with boundary the same as the domain of dependence of the boundary section A?
Boundary, not necessarily, because you can talk about, okay, that's a good question. So that's not trivial. For example, you can imagine this kind of example. Sorry, let me. Yeah, actually, this is the next thing actually related to next thing. So a little bit strange. Sorry. It's not good, right? Okay, this is probably okay. Okay, yeah. So we can write. This is a time slice. This is a time slice. And so you can choose subsystem A to be, this kind of doubly, this joint unit A1 and A2, right? A1 union A2, right? So that case actually entanglement which is non-trivial, highly non-trivial in that, like this. It's so so you can have this kind of, you can have you can imagine. So if we talk about, minimal surface, so entanglement which is like this, MA is like this. So it's highly non-trivial, right? It's different from the situation where, you have like this disconnected choice, gives normal, it looks like, boundary normal domain of dependence from the given boundary, but here actually they are connected in this way. So it's only, cut out this region. It's like, gets larger.
Which one is larger?
Huh? Yeah, this is real entanglement which is larger. Okay,
sure. Okay.
Larger than, this kind of causal wedge.
Right, but then if I, time evolve into the domain of dependence, and then so I sort of intersect that bulk domain of dependence with the boundary, I get a boundary, say, domain. Is that domain larger than the boundary domain of dependence of the original boundary section A?
Yeah, I think so. Original boundary of domain dependence is right. So you can talk about this and A1 and A2, no? Right, and let's see. So for example, this point is not allowed, right? This point is not domain of dependence, right? Because it can also come from here, right? You can connect, you can connect time like geodesic to this point, but this point also, included the entanglement wedge. So they are, I think that's large.
Thanks. Yeah, thanks.
Okay. Okay. So. Okay. Yeah. And before I go to this phase transition issue, I also want to mention one useful fact, useful idea, which is called the area operator. Okay. So at least up to one loop order, we find this formula, right? So this minimum area surface divided by 40 Newton. This is just same one, gyro. Holographic entanglement. And It's entanglement entropy, and so this is CFT, right? CFT entanglement, and this comes from CFT reduced density matrix exponential. And so here we introduce this, HA. Just we write, rho A equal to exponential minus HA, and this HA is a called modular Hamiltonian. This is a very useful operator. This is a Hermitian operator. And if we introduce this, then what we can say is this modular Hamiltonian in the gravity side, this operator, right? This operator is you can decompose this into two parts. First one, this area contribution, which is, if we can upgrade this to be area to be operator, because this is operator, this is also operator, this guy is operator. And this is called area operator. This area operator. And we can have some bulk modular Hamiltonian. CFT, right? MA, right? Entanglement, we have some entanglement with MA. Bulk modular Hamiltonian. Okay. And so this decomposition simply corresponds to this decomposition. So that way, anyway, so you can have you can directly relate modular Hamiltonian in CFT to bulk modular Hamiltonian, but there are small actually important difference which really come from edge mode contribution, which is namely area operator. But this is useful relation actually. We can use this just below. So before that, I would like to introduce another useful quantity. It is relative entropy. Relative entropy basically, measures the distance between two different density matrix. Rho prime, let's go rho and rho prime. This is defined. Rho prime, log rho prime. This is opposite sign, to on Neumann entropy. Maybe it is good to write this log rho prime, but we minus log rho, right? So this is called relative entropy. It's used many. This has a very nice properties, many ways in mathematical, also physical sense. But we should note first. We should note that this. It looks like basically this measures the distance between rho and rho prime. If rho and rho prime are the same, then this is just zero, right? Because these two are the same. But this rho and rho, this is not symmetric and the exchange of rho and rho prime. We should be careful. But this is nevertheless very useful quantity. And in this case, we can show. So by using this, actually, for this we can show basically distance between rho and rho prime, right? Sort of distance. It is not symmetric. And so we can show, but basically we can detect this distinguishability by using this quantity. But we can show that's the following very interesting equality, right? So this is rho in the context of area CFT. We can talk about two different states. We have psi CFT state, psi prime CFT, and from here you can get rho A density matrix, reduced density matrix rho prime by tracing out P, right? And then actually, interestingly, this guy is equal to rho prime. We are assuming area CFT. Here we are assuming area CFT. MA, right? So the bulk relative entropy is actually equal to a boundary relative entropy. This is a very strong statement. And let's see, let's explain why this is true. But first of all, to derive this, let's first notice that. Anyway, yeah, I just want to say this says that basically information, in entanglement wedge is equivalent to information of rho A, right? That means this is kind of establishment of the fact that there are bulk reconstruction, right, in both ways. You can reconstruct bulk from CFT, and you can reconstruct CFT from bulk, and so on. There are one-to-one correspondence because you can distinguishability is equivalent. And yeah, so but to understand this formula, so let's see rho prime. So there are very nice connection of this quantity to sort of free energy. So we can just rewrite this, right? Rho prime log rho prime, and let's take this difference of von Neumann entropy. So, but this is extra term, right? So we should erase this, right? Parting this, but the original contribution is like this term, rho prime log rho, right? And then you can regard this first one as a difference of entropy, right? You know, I mean, the usual entropy is log rho prime plus, you know, minus trace rho rho. What I mean here. And the minus, and let's see this one. This one is actually it's plus delta H. Right? What does this mean? So this is like rho minus rho prime, you know, log rho. But we can just put the minus sign here, right? Then rho prime rho and log rho, right? And the minus log rho is, you know, modular Hamiltonian, as we, you know, introduced here. Right? We introduced modular Hamiltonian here. This is so HA is minus log rho A. So this looks like this, you know. And this is like actually it's sort of free energy. You can think, you know, F equal, you know, this formula T minus Ts, but let's take temperature is normal to be 1, then this is E minus S, right? This is energy, you know, modular Hamiltonian is energy, and this entropy is minus. So this is much like, you know, free energy. So yeah, so entanglement entropy is sort of entropy, and the relative entropy is sort of free energy. This is a kind of generalization free energy, basically. So this is a basic connection, but yeah, this is useful to derive this formula. So let's derive this, right? Let's derive this. Yeah, so now we go. So we are interested in this rho A prime and rho A difference between, you know, two different CFT. And now we use this. Now we use this. Then minus delta S, right? Minus delta S. This A, right, plus delta HA, right? Well, both are CFT. And then this guy and this guy is minus delta area, right? This is just to use this one loop collected holographic entanglement entropy. And this is the bulk, right? Bulk MA. And plus, now we go this term. This term is given by this. And now we go this term, you know, like this. Then modular Hamiltonian already we found, right? Modular Hamiltonian we already found here, right? Area term and modular Hamiltonian, right? So this is there is an area contribution, right? And bulk contribution. Delta H is modular Hamiltonian, right? In the bulk. And if we and these two guys are cancelled, and only this guy appears. So delta H bulk MA minus delta S MA bulk. Right? So that way you find just rho MA. Sorry, let me a little bit save the location. So you find rho MA bulk and the prime, right? This prime and bulk MA, right? So obviously just bulk using this formula. Right? We use this formula, and this is bulk relative entropy, right? So and that way we can easily see this equivalence. In other words, you know, this formula already tells us their relative entropy and distinguishability are same. So this is the equivalence of distinguishability. Equivalence of there are many, you know, other distinguishability measure, right? Distinguishability measure, and this is just one example. But for relative entropy case, by using area safety correspondence, we heavily use area safety and holographic entanglement entropy. But then, if we admit that, then we can have some, you can prove this equivalence of distinguishability. This is a basic, derivation of entanglement wedge. Why, information corresponds between bulk and bulk. Okay, and yeah, okay, and the final part of this entanglement wedge issue, let me talk on phase transition. I already a little bit commented, but let me talk on phase transition. This is very important. And yeah, already we talked about phase transition phenomena of mutual information, and this is basically related to that. And just interpretation from the viewpoint of entanglement wedge. And so we consider the same thing. Consider rho AB, AB and A and B are disjoint, disconnected, disjoint subsystems, regions. Let me write a picture. I can write two pictures. And the first case, A and B are relatively small, right? A are separated. And the other case, they are very large. And they are very close to each other. Okay. And the first case, right? So we can write down minimal surface, and they actually disconnected, right? Disconnected. This is gamma A and gamma B, and gamma AB is actually simple union, right? And this case, and where is the entanglement wedge? Entanglement wedge actually is here, right? These two are MAB. This is the entanglement wedge. Okay. Now so entanglement wedge is disconnected. And the mutual information is 0. Right? And on the other hand, the second case, we have actually we have this connected minimal surface with gamma AB. You can have a disconnected one, but this area is larger. So we always minimize area. So we always have this. So, okay, and that case, entanglement is this full region, right? Very big region. Very big, right? So entanglement wedge is connected. So this is a opposite case, and there are phase transition between these two situations, right? Depending on the parameter, right? So A and B are apart. His case, A and B are close. So depending on the distance between A and B or size of A and B, and you have a phase transition. So mutual information, is 0 for disconnected phase, and the connected phase mutual information, it can be positive, is positive. So that way, entanglement wedge sometimes connected, sometimes disconnected. This kind of phase transition plays very important role. Also, this appears in many of my coming analysis, especially in the case of with boundaries. Okay, yeah. So anyway, these are basically, I just finished my explanation about the entanglement wedge, and I would like to move to boundary conformal theory and their holographic duals. So yeah, so maybe if you have some question, maybe it is good to have them maybe now before I go to another topic.
May I have one question?
Sure.
Yes, in the definition of area operator A hat,
Yes, yes, yes.
actually, what is the assumption there? A hat needs to be state independent. Right?
Yes, A hat is a linear operator. And yeah, state independent. And of course, that is only true for low energy approximation.
What do you mean by that?
So if we talk about, so we can calculate this area operator for many different states, some states, and but this state it should be included low energy Hilbert space. And only that case, A has a nice operator. It has nice property like linearity.
I see.
Otherwise, yeah, it's a bit really problematic.
Oh, I see. That's why you concentrate on.
Yes. Yeah. Originally, entropy is low, and we just pretend this is a kind of linear operator, roughly speaking. But this is actually state dependence because it's log. So in general, this is not true.
So does this mean that if we go to higher energy, then
yes, probably yes. We cannot have this description.
So we should say there is no area operator or A hat will be modified.
Yes, it should be modified in high energetic state.
So even at the high energy, we can assume that A hat is present. A hat exists.
In high energy, I think we cannot say that.
Okay.
Only low energy. And we fix some, for example, pure ADS and small excitation. We only talk about small excitation. In that case, we can use this description.
Oh, I see. So if we go high energy, then there are longer strings, and that would violate.
Yes, it violates, yes.
Something like that. Yeah. Okay, thank you very much.
Thank you for the question. Okay, so now any other question?
Can I ask you?
Sure.
Question? Is there any detailed form of area operator?
A detailed form. That's good. But that also, I don't think we can have so simple formula. You mean probably formula from CFT side, right?
Yes.
It's not that so simple in general, I should say.
I just wonder if we exponentiate this modular Hamiltonian equation, then we can, in principle, we should be able to write CFT reduced density matrix in terms of bulk reduced density.
Yeah, you're right. But what I want to say is that if you talk about this part, is easy in some sense. This part is easy because this we have some area law divergence, right, for entanglement entropy. And if you excite a little bit, you have some small finite, some shift of this entropy, right? That part is precisely this, right? And this part, I think, is relatively easy to find some formula. But this part includes full UV divergence. And that part, I don't think we have a so simple formula. Except some free theory. Free CFT, yes, but free theory is not dual to, this gravity, right? You cannot apply this CFT. Free fermion or free boson, we cannot apply this CFT. So in general, strongly coupled theory, we don't know how to write down a hat because also at the same time, we don't know how to know precise spectrum of the theory in strongly coupled theory.
Thank you.
I want to ask the phase transition of entanglement wedge part.
Yes.
And it is bounded by the gamma A and gamma B. Is there any difference if gamma A is classical or quantum extremal surface?
You can. If we talk about really, you are interested in very quantum region, so gamma A should be quantum extremal surface. That is true. But of course, that case, it's not so easy to calculate many things.
Okay.
And if we really, has a lot of quantum effect, like really non-perturbative situations, space-time is fluctuating, so we cannot even write such a picture. But I'm talking about just some classical. There are some classical gravity limit, and we talk about some expansion, right? Some perturbative expansion of quantum effect from that case, we can apply this kind of phase transition phenomena. But that case, we have to sum over all perturbative series and to define quantum extremal surface. But very abstract.
Okay. Thank you.
Could I ask?
Sure, yeah.
Could you comment how about the H mode for the gauge field? Is there any error operator for gauge for U1?
Okay, yeah. I think you're right. I think basically you can area operator is sort of super selection sector of some each Hilbert space. Basically, edge mode come from that, and the gauge theory obviously have a super selection sector. And indeed, there are several papers which derive some formula of entanglement entropy for gauge theory, and which looks like area operator, looks like this operator. Yeah, it looks like this, and because you can start with the Radian gauge theory, right? And talk about separate contribution to entanglement entropy. So separate entanglement entropy to two parts. One is a purely entanglement, right? Purely quantum entanglement, and plus some super selection sector contribution. And this super selection sector contribution precisely take this form. And that's a nice matching with by using ADSFT. Right? In gauge theory side, Radian gauge theory you have, right? And you have some decomposition like this. And also gravity side, we have this decomposition. Both agree, basically.
So in this sense, you can extend to the higher spin gauge field, can also construct a so-called
higher spin. You're talking higher spin.
Yeah, not only.
A higher spin case, right. Okay. Yeah, I think so. Yeah, higher spin case because also it is dual. It's supposed to be dual to some Radian theory, right? And they maybe have such a structure. So may have that, but it's not area. The gravity side is not area for higher spin. Gravity.
For U1 is error, as you said.
Sorry, U1?
U1 gauge field.
U1, you are talking about U1 gauge fields. U1 gauge fields, we don't know, right? Gravity dual, right? So I'm not sure. We have such a simple decomposition.
Oh, I see. You mean you talk about the
I'm talking UN, SUN, and Radian limit. But essentially, U1 case also still you have this kind of decomposition because you have a flux sector, right? And that is a super selection sector. But I don't know how to interpret in holographic way.
I see.
Okay, yeah, but roughly speaking, what you are saying, you can have such a structure engaged. Okay. Okay, no more question. Okay, so let me go on. But here I just choose different. Okay, I think this one. Right? Yeah. So I'm going to use some slides here, but sometimes I write it. And if you have a question, I will write something to explain. Okay, so now I go to this section 5. So I would like to explain this holography for boundary conformal field theory. I'll explain what this one quickly later. And then also this is directly related to recent application to black hole information paradox. Okay, but I think anyway, in this morning, I will basically talk about this issue, holography for boundary conformal field theory. So let me start with BCFT. So this is a boundary. Anyway, I will also post these slides to Slack, so you can use it later. And this is a boundary conformal field theory. So this boundary conformal, please do not confuse this with standard ADSFT. ADSFT means gravity on anti-Doshita space dual to CFT in the boundary. But I'm not talking about this boundary CFT. I'm talking about CFT where CFT defined on a manifold with boundary, like disk. Right? You can also think about some disk. In 2D CFT, you can talk about 2D CFT on a disk. Then obviously you have a boundary, right? So let's forget about the CFT. Just CFT already itself has a boundary. So this is a boundary for compute set. But you can, in general, you can choose any boundary condition, but there are some special nice boundary condition. And by using that boundary condition, we can define this boundary compute set. And so CFT do D-dimensional conformal field theory, as you know, you have a SO2 comma D symmetry, right? This is conformal symmetry. And but if we put the boundary, you need to break some of them, but you can actually keep some part of that SO2 comma D minus 1. If you talk about, if you are interested in SO, actually 2D CFT, it's like SO22, right? SO22 is same as SL2R cross SR2R, right? And you have left moving Virasoro and right moving Virasoro, left and right. But if you have a boundary, we only have a one linear combination of that, only you have one SL2R. And this is exactly this one. This is same as SO21, okay? And so this is a definition of boundary conformity. This is the special boundary. And we can also regard this boundary as a state, because we can regard this as time. Sometimes we can call this, here it's a Euclidean time. And then, space-time started with some boundary, right? In that case, this boundary defines some quantum state, because this is a wave function, right? You can remember our calculation replicatory. This gives some quantum state here after path integration. And this state is defined, it's called boundary state. This is called boundary state. This is called boundary state. Sometime we mention later. Okay, so and we write it B alpha. Alpha is important because alpha is a level of boundary condition. You can have many different boundary conditions. You have many different boundary conditions and labeled by alpha. Here. And so for in 2D, right? In 2D case, this kind of boundary state is well studied, and it is called Cardi states. Cardi states. And satisfy this Virasoro condition. The Ln is a Virasoro, left moving Virasoro, and Ln tilde is a right moving Virasoro, and it satisfies this condition. This is precisely same statement that we should keep one linear combination of Virasoro. And if we talk about the disk amplitude, like you can insert some operator here, this is equivalent. You can calculate this as inserting this boundary state, right? Because we can put some operator here, the same, right? Then, and we can attach vacuum state, and this is the conformal map to this disk, and we can calculate amplitude like this way. Anyway, this is a boundary conformal field theory. And for example, simplest example, you can imagine you can talk a massless scalar field, and you can just impose Neumann or Dirichlet boundary condition as a boundary, then that also defines boundary conformal field theory, the example, basic example. So then the next question I'd like to ask, maybe I write it before let me write it here. Okay, so next question is obviously, it's what about holography? How we can construct holography dual? So here is a basic construction. So we have like some, some manifold, some disk, for example. You can talk about this boundary CFT. This is boundary. So we have BCFT defined on this manifold. I don't know how to, what's the name? A, we call it A. Okay, let's call this A, and this is a boundary. This is a boundary. There is some boundary. And yeah, inside is a boundary conformal field theory is defined. And this is a CFT side. And what about gravity dual? So gravity dual, actually, we do some extension. This is much like, you might think this is a little bit similar to holographic entanglement entropy, but actually naively similar, but it's actually so different. I will explain. But the picture looks similar. So we can extend towards bulk, right? This is not, actually, this is not necessarily minimal surface, some surface, which is defined later. And this surface, I think we call it Q. This surface is Q, it's called, and this is a bulk, right? It's a bulk areas. But it's cut it out by the surface Q. This is I think it's called, yeah, okay, let's see, M, okay, let's call this M. This is a bulk region, and you can think this is a Z direction, extra dimension. And this is originally in the ADS safety language, you have some boundary, right? Originally boundary. Boundaries of, you can talk about maybe one metric, then it's like flat space. And the basic idea is to extend, this really boundary of CFT to bulk. And so let's do this ADS. Let's take. Sorry. Okay. Yeah. ADS D+1, and this is Q is a D dimension. Previously, in holographic entanglement entropy case and surface, minimal surface is D-1 dimension, but here it's D dimension. So dimension is completely different. And of course, this bulk space is in D+1, and the BCFT lives on D-1 as a D dimensional manifold with boundary. Right? This is a boundary, and this boundary is D-1 dimension. Okay. And so this basic claim is that this BCFT is dual to gravity on this manifold, this inside of this surface Q, not full ADS. Okay. Another question is Q defined? Okay. As a fixed going. Okay. Let me explain how we can decide Q. There's a question in the chat. So this question Q actually we determine this Q by imposing fixed by Neumann boundary condition in gravity. This is a simple short answer. And this is we'll explain. So we okay, but before that, just let me write down the claim. So this is a dual, right? Dual, holographic dual. This is what I call ADS BCFT. Okay, but I think the question is about what about this, right? How we can decide, boundary conditions. That's quite important. So let me explain. So here is a more detailed picture, the claim. Let me repeat. So we are talking about CFT on a manifold A with boundary partial A, right? And this is ADS BCFT argues that this is equivalent to gravity on asymptotically untitled zeta space M, right? And such that this manifold A ends on the A, boundary A, and also Q, surface Q, right? And the question is how we can decide this surface Q, right? You can choose any, and the entanglement entropy case, we choose minimal surface, but this is not happening here. We have different equations given by actually Neumann boundary condition. And the important ingredient is, of course, normal vector, right, of the surface Q. And by using normal vector, we can define so-called intrinsic curvature, right? So how this surface is embedded in the ambient space, right? So how this is curved. And it's basically covariant derivative of this normal vector and the parallel projection down to parallel to this surface Q, right? And the KB is an extrinsic curvature. This appears in many times, so please remember. And the K is just trace, right? Just trace of KB. And by using this KB, we can write down so-called Neumann boundary condition, which is like KB is basically 0, but actually sometimes we can put also some matter, localized matter on Q. So this looks like Einstein equation, right? If this is Einstein tensor equal to energy momentum tensor, but this is actually boundary energy momentum tensor, and this is a kind of boundary analog of Einstein tensor, KB. This is very familiar, actually appears everywhere, many times in general relativity. And also I will explain this more later. But another comment, this surface Q is really terminating space-time, right? We really end and with boundary condition. And such a surface nowadays called end of the world plane. End of the world plane. But anyway, the same. I just write it to Q, simply write it to Q. And so the reason why we impose Neumann condition, I will explain. But this is actually we can just follow the idea of this Landau-Sandler model of brain world, which also we use the idea of a Landau-Sandler brain world later. But here just technically we use the idea. So we keep, and the physical meaning is like this. If we impose Dirichlet boundary condition, right? If we Dirichlet boundary condition means just fixed metric, right? But this is not good here. So we usually impose Dirichlet boundary condition in the ADS boundary, right? Of course, because we are interested in CFT on particular manifold with particular metric, right? So we impose Dirichlet boundary condition here, but we don't want to impose Dirichlet boundary condition here. The reason is that we want to keep boundary to be very dynamical. There are some kind of fluctuating also. And on the boundary side, we need to fix metric on this partial A and A, but this part is completely holographic direction. We don't have any even candidate of the metric right? I mean candidate metric which is used for fixed metric Q, right? And also another, you can imagine some particular example in string theory, and especially one example is like something orbifold-like situation, like more precisely orient fold. Now orient fold is come from defined by identify left side and right side, G2 identification. And if we think this condition, actually this G2 symmetry is equivalent to this KB is 0. This is 0. Because symmetry. If you have symmetry, curvature should be 0. No curvature. So that this is 0, but it's a very special example. But this also suggests this form. That is true. And there are one more reason why we originally think this boundary condition. I will come back. But before that, let me emphasize that there are two differences between. There are very, important difference between entanglement wedge and ADS-BCFT. So I just explained entanglement wedge, right? And entanglement wedge, we talk about some region A is dual to this region is dual to some region, right? That's right. And then we talk about so what we find, we have like density matrix, and just we did it the bulk density matrix. They correspond to each other. And this case actually boundary is very artificial, right? We don't need to introduce this boundary as a theory. Just we introduce this boundary as a kind of artificial way of cutting Hilbert space. You can choose any different boundary, and actually original physical theory lives on the full space. Always original theory lives on this plane, right? An artificially cut space. And in that case, this region information included this region is dual to this bulk region, which is called entanglement wedge. It's surrounded by minimal surface. This is minimal surface. And the minimal surface, if you rewrite minimal surface condition by using differential geometry, it's just trace part of extrinsic curvature is 0. Right? This is just minimal surface condition. But on the other hand, in our case, right, we are talking different thing. We are talking about literally restrict space into this region, disk region. And we get rid of other region. Physically, we impose boundary condition. And in that case, how this theory is dual to, right? What this theory is dual to, and this theory is dual to some region surrounded by some surface Q. Now this is different from gamma A. Now also, also dimension is different. This guy is dimension D minus. Let's talk ADS D plus 1. Then this is D minus 1 dimension, and this is a D dimension. This dimension is also different. But also, this surface has a different character because KB is fixed, right? Like this way, we fix KB. This is a kind of over constraint. This is a kind of over constraint. We should be careful. That means actually, sometimes we don't have any solution. And in that case, what we do is just back react geometry. This is a kind of real brain. This is a real physical brain. So I want to emphasize this is physical brain. This Q has a tension and it has a physical brain. But this guy, this gamma A is not physical in some sense. Just we introduced by hand. Kind of probe, just put by hand. So this is physical brain, so it's back react, so it can change the metric, and that's the reason we can realize this condition, this over constraint. So we have to solve Einstein equation and this boundary condition at the same time. So this is what's happening here. So that way, so these two guys are so different. Sorry. Yeah, here. So that way, so these two guys are so different. There actually equation is Q codimension. This Q is codimension 1 because its total space is ADSD. Okay, ADSD plus 1 codimension 1. This is a codimension. Okay, Q is codimension 1. Let me write it here. So this is a codimension 1. This guy, gamma A is codimension always to entropy is always related to codimension to surface. What's the holographic dual of strip? Actually, I think I will come back this later. So I think please wait a bit. I will do that. Yes.
So in the BCFT side, what's the boundary condition on DA?
Good question. That's kind of implicit, I should say. We can just take care of any boundary condition which satisfies conformal invariance. So yeah, we just require only symmetry argument, and that kind of boundary we can treat in this way. And because this has a parameter, right? We can choose. Actually, we have like degree of freedom by changing this T energy stress tensor. And you can choose different profile of Q. You can put some tension, or even you can put some scalar field on Q, and there are different variation. It's a lot of variation, and that variation corresponds to different boundary condition on A. So, but I cannot give precise map because to have such a mapping, we need a precise string theory realization, and that we can have some particular such example. But except that, it's not. We should be kind of ambiguous. That part is implicit.
Okay, thank you. Another question is this TQAB is the stress tensor on Q?
Yeah. Oh, exactly. Stress tensor on Q. Yes.
And it's supposed to be including all quantum corrections, or?
Yeah. But I'm working on classical gravity dual. I mean, classical level, to be honest, so far. But in principle, yes, we should include higher order corrections.
Okay, thank you.
Yeah, thank you. And there are also another question. For a theory defined in ADS PCFT, is the theory outside the Q physically undefined? Yeah, physically ignore. So there are nothing. What I mean is just, space-time is only this guy. This is only for whole space-time. And we cannot even need to talk about outside region. This is a ADS PCFT.
Excuse me, Professor, can I ask you
Sure.
one question further? So, in ADS-FT, we know the conformal symmetry is due to the ADS isometry of the space. So I'm assuming like now you have the boundary for the A, which is for which the symmetry is a subgroup of the conformal symmetry. And so I naturally would assume is the surface Q somehow determined by a subgroup of the ADS isometry, which preserves the Q?
Yeah, I think you are right. Yeah, actually, that's right. You are right. So actually, this condition, actually, I will give more specific example, but you are right. And this K is highly related to symmetry. For example, if we talk about KAB is 0, right? Then this should be supported by symmetry. And in that sense, Q should be automatically says ADS2 inside ADS3, for example.
Okay, thank you.
You're right. Yeah, and, it's related to some symmetric. Yeah.
Okay, thank you. And how about the we know the Z direction is sort of the UVIR direction of the field theory.
Right. That's right. Yeah, radial direction.
It still holds in this picture.
Even UVIR duality. Yeah, the same. Anyway, if we talk about the boundary, anyway, we integrated the boundary, right? So infrared information boundary is reflected to some profile of here, and the UV property of boundary condition is reflected to UV region.
Okay. Thank you.
Yeah. Good. Okay. Yeah. Okay. Then can go. Maybe one more question. Let's see. What's the meaning of no need for new data on Q? Okay, so where do I write that? No need for. Yeah, okay. So yeah, we don't have any candidate of metric. If you want to import some, if we want to import Dirichlet boundary condition, we need to specify metric right here, but we don't have any candidate. But if we Neumann boundary condition, we can just import this. Right? Maybe you can even set this 0. So I mean, we don't need new data. That's basically what I wanted to mention. The things becomes more clear if I talk about, if I give us a more explicit example of TABQ, I think. Okay, so let me. So anyway, this is more detailed. So we can have some in this action in gravity. We have like this bulk contribution, right? Einstein-Hilbert action and the cosmological constant and the boundary. If we talk about boundary, the surface. So let me write it down again. So this Q is this surface, right? Q is this surface. Q is this surface, and here it's boundary A is here, right? And like this way. And this N is like this. Sorry, this is maybe I write it to M, but it's here. Here currently M is the part. And so this is just standard Gibbons-Hawking term, right? And this is matter. Also, I put some matter on Q, right, to have to realize different boundary conditions. Okay, and then we define. Yeah, this is the same one. Yeah, extrinsic curvature. And one simple example of extrinsic curvature is like you can assume this kind of Gaussian coordinate, like B rho, and we can assume always we can use some sort of coordinate transformation, and we can always rewrite metric in this form. And once you have this form, then extrinsic curvature just directly computed this way, just derivative of this guy. Okay, and the crucial point, what I want to stress that we can take a variation of this, and of course, so this part gives Einstein equation, right? But for variational principle, we need to impose also variation at the boundary also should vanish, right? Variation at the boundary is given by this, at the boundary surface Q, you get this, I mean, when we change the metric, we have this variation. This should be 0. Indeed, this is the reason. This is the reason why we import this Neumann boundary condition. Dirichlet boundary condition is like this is 0. Right? We should impose either Dirichlet or Neumann, and we just chose Neumann boundary condition. This TQAB is just come from this part. Right? This is very abstract. Matter Lagrangian gives by taking derivative metric, we just get the boundary energy stress tensor. So that way we encounter this boundary condition. Okay, so then this is kind of analog of boundary Einstein equation. And so yeah, so we impose this Dirichlet, not Dirichlet, but Neumann boundary condition. Okay, and so in summary, so we need to solve Einstein equation and also this boundary condition at the same time. So that means even bulk metric can be modified, right? In general, different from purely ADS spacetime. Okay. Here we go. And then, so I now go to basic example, which is ADS D+1 and BCFT-D. And so in general, I said this TQAB just come from, matter localized on surface Q, right? But actually, there are some nice class that are also related to this previous question that we should choose some, nice boundary conformal symmetry. Then actually we impose, boundary conformal theory as we assumed from the beginning. So that case, actually, this boundary conformal symmetry is very strong constraint, and actually we can see that this TQ should be proportional to HAB. Right? This is kind of, in that sense, this, if you remember this formula, this is much like HAB. So it's like a cosmological constant, right? It just looks like, again, boundary analog of Einstein equation for untitled space. So, but the difference is maybe T tension can be positive, even positive and negative. Both signs are possible, as we will see. But T is just constant, and T is just tension of brane, right? Just tension brane. So it's back reacts because it's the tension, it's back reacts. Okay, and then so Neumann boundary condition looks like this. This equation we can just rewrite by plugging. It looks like this, and we can easily solve this. And it's just KB is proportional to HAB and proportional to T tension, and its coefficient fixed by this. Okay, so there are some. I just noted one question. The matter theory defined on Q as Q extends along the defined on Q. What energy scale does matter theory? Right. What does it look like? Yeah, so you can just regard this matter theory on Q is the same as matter field in the bulk. Right? You can put sometimes scalar field to calculate a scalar operator 2-point function. In the same way, you can put some scalar field on Q. And this the idea of energy scale is the same, right? This is if we put some scalar field, at the classical way, then it's like just supergravity approximation, as in the bulk theory. Does this answer the question? I mean, even if this is boundary, we have boundary, but the same as bulk calculation. Okay. Yeah, and then the gravity action takes this simple form, right? And this is, and yeah, just I simplify this part, right? Putting tension. This is just tension. Tension times square root h. Right? It just looks like this. This is a boundary. This is a Gibbons Hawking term, and this is a matter contribution, and this is an Einstein-Hilbert term, right? Then, so now we would like to construct a gravity dual of boundary conformity theory, and in this setup, so this is actually very, very easy. So we can easily find solution. We can just construct it. This is shown here. And we have like, yeah, what we had in mind is CFT with boundary, straight line boundary. It's just plain boundary, right? And this is the W direction. W is sort of, one space direction. Time direction is, I mean, you can imagine time direction is also gonna to this seat. I don't write time direction. So the X direction is here. There are two space direction, X and W. And the X direction, space-time terminates, at the boundary. This is a boundary. And this CFT is dual to some part of untitled space. This case, we don't need to worry about back reaction because this is a very beautiful example, and there are no back reaction. And that case, we have, this is the extra dimension Z, right? This is the untitled space, this is a boundary, ADS boundary. ADS boundary is here, right? This is a boundary. And this is extra dimension, and so always CFT lives on the boundary. So, but this is this part. Okay, this part. I just write it here. This A is here. A is of course full space, but this is here, situated here. And the boundary, this is just originally this point, right? This boundary is just this point, but they extend to the bulk. This is a surface Q, right? This is a prescription of ADS BGFT, extend. In general, complicated, but this case is just simple one, a straight line, straight plane. And inside is a gravity dual. And this is what we have here. But there are useful coordinate system called rho, and this is kind of hyperbolic slice. It's a hyperbolic slice. So you have a ADS D+1, right? But you can have a slice where we have on each slice metric looks like D-dimensional untitled space. And this case is warp factor is cos rho square, and rho is this coordinate. Rho equal -infinity is just this boundary, and rho gradually increasing, and rho equals 0 is really this vertical plane. And it's go this way, positive rho is going this way, and rho goes to infinity, we plus infinity, you get this surface, half of that. Right, this go this way. And we terminate at some rho equal rho star at this point, right? Then we have this space. So this is a gravity dual. And so we can write this metric in terms of just standard Poincare metric, right? Like this way. And the connection between rho coordinate and this Poincare coordinate is given by this, right? Rho and y. Y is this, this metric is given by this. Y is the radial direction of this patch, radial direction. Y is this direction. And the y and rho is related to z and x. Z and x of this Poincare coordinate, z and x. Right? Y and rho is related to z and x by this formula. This is a very famous formula. Okay. And yeah, so this part is given by this metric. And that way we find concrete, description. And indeed, you can confirm, you can evaluate extrinsic curvature on this, surface Q. and just take derivative of this guy, right? This Gaussian normal coordinate, we can just take derivative of this guy and we get tangent. And from that, KB is non-vanishing, and you can compare this with this one, and we get 2, right? Just one. We can just compare this way. Then we get this tension. Then we get this tension for dimension D. So rho star 0 means just symmetric pattern. D2 invariant surface corresponds to tension equals 0. Right? Tension, as I told you, so KB equals 0 condition is symmetric, Z2 symmetry, all before like plane. So it's like this. And as tension increases, this surface Q goes this direction, and the tension decreases if go. And the region is very small wedge.
Can I ask you?
Yeah, sure.
How can we understand there is no back reaction to bulk in the
good
view?
question. Anyway, the idea is, we just assume this is a correct background and calculate KB, and it really satisfies the equation motion.
So this is not a unique solution?
I think, this is unique. This case is, I think, unique, but because of the symmetry. Anyway, we are talking about this kind of solution, right? This solution should satisfy some sort of SL2R symmetry, right? Because the boundary have SL2R symmetry. And because of SL2R symmetry, this answer should be true, right? Because it's an ADS2, right? If we talk about the ADS3, so we have some structure of ADS2, right here. And then you have SL2R, right? And we know boundary conform field theory has SL2R symmetry. So we should have such a slice. Yeah, that's actually come from symmetry argument. Yeah, more properly says.
So this is Poincare metric, and it's not a global
no.
And
but
it's
if
also
you
based on the symmetry argument.
You can, if you are interested in BCFT on compact manifold with boundary, then you should use global radius. But here we are talking non-compact half plane, so it's quite natural to start with Poincare, right?
Thank you.
Okay. Good. So, this is important actually. This is because the reason we put some ADST is symmetry argument, because it's by BCFT preserved symmetry part of it. Okay, so now this is a basic example of ADS BCFT, and I already gave also basic construction of ADS BCFT. I hope you had some feeling how to do this. And now we would like to move on to this entanglement entropy. Also, this is the main topic of this lectures. So what about holographic entanglement entropy, right? So this is again related to this. I work with Fujita and Tony at 2011. And anyway, we can actually give a simple prescription how to calculate holographic entanglement entropy in the presence of this boundary surface. The only non-trivial thing, this is a surface Q, right? This surface Q. This picture is the same, and this surface Q. And the only non-trivial thing how to treat, this surface Q. And the answer is given by this. This much. This has had in mind some covariant formulation. Let's see for covariant. You remember covariant formulation exactly takes the same form, but there are no B here, right? Yesterday I explained covariant entanglement entropy is the formula without B, but now we also put B. So what's happening is here. So we have ADS BCFT setup. We have a boundary surface Q. Boundary CFT lives on this manifold M, right? Sorry, I changed many notations. I'm sorry, but this is a boundary manifold, and the subsystem is always A here. And we want to calculate entanglement entropy. Usually we calculate minimal surface area, right? But now point is that we have this, extra surface Q, Neumann with Neumann boundary condition. Dirichlet, not the Dirichlet, but this Neumann boundary condition. This case actually this minimal surface which come from A can end on this surface Q, end over the world plane. also you can choose the one which does not end. That's fine. But if you have some surface which end on B and which has a smaller area, you should use that one to calculate holographic entanglement. So that sense, and this choice of B is arbitrary. So that is we minimize over choice of B. In that sense, so then we should ask, what about homology constraint, right? Homology constraint means this surface, gamma should be homologous to A, right? But if we have a B, it doesn't look like so. Yes, but that doesn't look like satisfy, do not seem to be satisfying homology constraint. But the idea is surface Q, once we impose Neumann boundary condition, this is nothing related to any Hilbert space. This is very also crucial in this island story. The Q is topologically trivial. Even though mathematically this is not topologically trivial, but in physical, we think everything related to Q is topologically trivial. This is an assumption. And by that way, we define homology constraint. So you can choose any B. So that's the idea. So you can even end on Q. And still, you can claim this homology is the same as this connected one. So this is the assumption. Anyway, but once we take into account that assumption, we can define this formula, and this perfectly reproduce known behavior of holographic entanglement as a known behavior of entanglement and computed already in some condensed matter people or quantum field theory people computed entanglement entropy in the presence of boundary, and this formula precisely reproduce all such results. And yeah, so this holographic calculation is same as this situation with CFT lives on the manifold with boundary, right? And we talk about subsystem A and calculate entanglement entropy, but we can calculate as this kind of area. This is a claim. And this region B, extra region B, is nowadays is called island in the context of black hole information paradox. Okay.
So, excuse me. So in this case, I suppose A is quite near the boundary.
Sorry, could you say that again? Sorry.
I mean the picture here.
Yes.
I suppose A is quite near the boundary of
yes. Yeah.
So if it's far from the boundary, I think it's the picture should be different. Right?
You are right. They are very natural. Indeed, that's important. And if A is far apart from the boundary, okay, so the color is let's A is then minimal surface is just standard one because it's far from Q. Yeah, you're right. So if A approaches the boundary, so we have some such a phase transition that we get the non-trivial. Yes. Okay. And okay. So let's see. Yeah. So these are some connection. I'll come back to this again, but this connection I think also discussed by Henry Masfield, I think in his lecture. So I'm very brief about this. And but this, there nowadays people talk about this island formula to calculate entanglement entropy in the theory with coupled to gravity. I will explain why this is related to gravity. I mean CFT coupled to gravity later. Maybe next lecture I will probably explain this. But anyway, so we have some CFT lives on the subsystem A and calculated it like as I explained. So this is the end of the world plane and we connect this. And the island formula takes this form. Right? And the formula takes this it's a black hole entropy part as not exactly black, but this region is called island and just compute area plus entanglement entropy, but entanglement entropy computed with this A union this region B. Right? Sorry, in this case, this is same as island. Okay. But, okay, yeah. Anyway, we union A and the island region, and this calculate entanglement entropy, and this minimization. This is known as the island formula, and worked out recently by Pennington, Armenyi, Engelhardt, Marov, and Maxfield. And yeah, quite recently. And but here we can decompose our ADS BCFT calculation. We can cut this point, roughly speaking. This part actually compute this quantum part, and the final part, this nearby brane contribution basically gives area contribution. So that way they have a one-to-one correspondence in this calculation. Okay. Okay. So now it's time. It's almost. Ending, I think. So, okay, so maybe What should do? Okay. Let's see. Yeah, let me just mention this slide and finish it. So from that, I'd like to talk about the quantity called the boundary entropy. So yeah, main part I will discuss this in next lecture, afternoon. And but here I just wanted to mention that. So let's focus on D equal 2 case, ADS3 BCFT2. And we have like previous one, boundary CFT lives on the boundary. And if we regard this time direction, this looks like state, right? This state is called boundary state, satisfy this Virasoro condition. And the correlation function, we can rewrite this way. And this is something I already mentioned, right? So disk means you can have just a sphere with hole, right? Is a disk, right? Making hole is described by this putting, inserting boundary state is making hole. And here the important quantity is boundary entropy. And that's what we would focus on, because this quantity is very actually related to this is some part of entanglement entropy. So this is very closely related to entanglement entropy. And this is also nice quantity because it's a measure of degree of freedom at the localized at the boundary. And there's some well-known theorem called G theorem proven by Frieda and Konecny, and originally introduced by Affleck and Ludwig. And the G theorem is sort of a boundary version of C theorem. C theorem means the central charge decreasing under RG flow, and G theorem means boundary entropy G function. G is actually decreasing under boundary RG flow. Boundary RG flow means in the bulk we have conformal imbalance is maintained like exactly marginal. Sorry, no perturbation in the bulk, but only boundary we have some perturbation, and that triggers boundary denormalization flow. In that case, central charge does not change, but the G function decreasing. And this is this G function is also called boundary entropy. And I will, I think, discuss this later, and this is definition and so on. Okay, yeah, I think I will stop here. And there are actually questions. Sorry, I just noted one. Sorry. Good question, maybe. A is a subspace time region of subspatial. Subspace time. A. Here A is, sorry, this A is so we take a time slice here. Time slice. We take a time slice, so it's like a spatial. A is a spatial surface. This is the one question and the one answer. And another question: does this phase transition when A approaches the boundary related to page transition? Yes, that's right. Yeah, that's exactly true. That's I will come back later. And can Q extend inside horizon? Can Q extend into the horizon? Let's see. Q. Q is time direction, and yeah, that's right. Yeah, this is also true. Yeah, there are some simple setup. You can think this Hartmann-Malazan setup. This is the original sum field double, right? Sum field double, and we have CFT1, CFT2. And in this case, you can introduce surface Q here. So then it's really inside the inside horizon. Yeah. Okay. Yeah. Anyway, yeah, I'm done for this morning session.
Thank you, Tadashi, for your excellent lecture. Any more questions?
Can I ask?
Yeah, please.
Yes.
Can I ask you?
Sure. Yes.
What is the brain tension corresponds in the safety point of view?
Good question. That's actually my next talk, and this is related to boundary entropy, actually. And boundary entropy is a kind of monotonical function of tension.
So given a safety with a boundary, so what does a boundary entropy depend on?
boundary entropy depend on. Okay, but it's
When
okay.
we
It's
consider chains or
it's a kind of disk amplitude. I'll explain just next, but if you have a CFT, you can, of course, you can calculate disk amplitude, right? Disk partition function. That's actually it gives, but we need to remove divergence. But after removing after we do some proper renormalization procedure, then you get boundary entropy.
okay, thank you.